All right, so this is going to be part 3 of my saltwater wedge series. And we're just going to talk about, let's see, so the first one was we talked about pressure, where the entire point of the pressure thing was that P equals rho G times the depth. Then we talked about, so we used that on the second video to talk about the so-called estuarine circulation, wherein water that is sloped at the surface and flat on the bed. Hold on, Rocky is going nuts. He is climbing all over everything, so you might hear me holler. Where we can combine two types of the, I guess, pressure gradients. The one being we would call barotropic, which would be due to the fact that it is steeper over here. So H in the fresh water is greater than H in the salt water, so it is deeper over there. And we can combine that with the fact that, there is a sorry, I don't know if I call that this is the blue, this is a, sorry, Rocky's being nuts. Okay, so the blue is barotropic and the red will be baroclinic, if I can get red. Okay, the red will be baroclinic, where there is a pressure gradient due to the fact that the density of the fresh water is less than the density of the salt water. So if we imagine the density of the salt water is over here, the density of the fresh water is over here. Okay, so anyway, so when you combine those two, you end up getting this circulation where the water goes in along the bottom and out along the top. Wait, Rocky, please, do you mind? Do you mind? Just chill out. Just chill. Okay. All right. Good boy. All right. Okay. So we'll get that sort of out over the top and in on the bottom. Okay. Sorry about that. All right. So now what we're going to do is I'm going to basically redo 1 and 2, or redo basically the effects of 1 on 2, but I'm going to use calculus to explain all that. Okay. So here's what we're going to do. So I'm going to set up my imaginary system. So I've got, a sloping free surface, and I've got a bed. Okay, and so at any given point in this particular thing, I can calculate the pressure. I can say, oh, well, P equals rho times G times the depth. Okay, and so the way that I've been measuring the depth in this particular bad boy is I've been saying, like, okay, well, this is the depth, right? The distance from the surface. Okay, so if I'm going to use calculus for this, I'm going to, so I guess what I'm trying to drive at here, and what I did earlier up here, for example, is basically I said there were two pressure gradients and I'm combining them. And now what did I mean by a pressure gradient? Well, what I mean is basically the difference between the pressure upstream and the pressure downstream. Okay, and so ultimately this is one representation of the pressure gradient at a given point. So this is how the pressure is varying in the x direction. Okay, so that is the pressure gradient. So if I'm going to do that down here, I need to have, some axes. Okay, and so we will define these things. I will define the axes. Let's do, green. Actually, I think if I remember correctly, green doesn't show up very well. So let's do blue. So here's my x-axis. Here's my x-axis. Okay, and then because of convention, I'm going to call this my z direction. Okay, so this creates a problem because my depth is measured vertically downward, so it's kind of like in the negative z direction. Now, I should mention this before we go on. You may be more comfortable with, instead of z, you may be more comfortable with y. But we're not going to use y because by convention, most of the fields that are done in this, they use z. So, hate to say it, but, just kind of get over that because we're not going to be doing that. Okay, so anyway, so z is just our vertical component, or our vertical coordinate. And so the problem here is I need h to be defined, this depth thing, I need it to be defined in terms of z. Okay, so here's what we're going to do. I'm going to define the total depth of the fluid from the bed to the surface as capital H. Okay, And the reason we do that is because then that gives us a nice expression for lowercase h. Okay, so lowercase h equals capital H minus z. Okay, and I think if you look at this image over here, you can see that for any location, we've got a depth h, and we've got a vertical coordinate of z, and then the difference between the two is this h. Okay. All right, so now I've got this equation right here. Let's see, here's my equation, and I guess I'm going to put it right in the middle here. P equals rho G, and in place of H, I'm going to make H minus Z. Okay, so this is the pressure in anywhere in this fluid, really. So that's the pressure here, that's the pressure here, that's the pressure here, that's the pressure here, that's the pressure here. As long as we assume that the rho is constant vertically, which of course is it isn't usually, but usually the difference isn't very large in an estuary. Okay, so what I want to do now is I want to say, well, how is this pressure varying in this x direction, right? So how is it varying as I go from somewhere over here to somewhere over here? Okay, and so the way we do that is I'm going to say, how does the pressure vary in the x direction? Okay, so I'm looking for the derivative of pressure in the x direction. How is it changing? This is the exact definition of a pressure gradient. Okay, and so to get that, I need to get the derivative of this whole thing right here, rho g h minus z. Okay, and there's two things that need to be known here, or need to be mentioned here. Rho changes with respect to x. Okay, g does not. Okay, maybe I'll underline the things that do not. G does not. Okay, h. Okay, remember what h is. H is the total depth here, from here all the way up to here. Okay. And we can see that as we move in this direction, that total depth is changing. So h right here is a function of x. Okay, and we will note that the z direction, or the z coordinate, does not change in the x direction, right? So I can move along this way, and my z coordinate does not change. Okay, so that's important because for those of you guys who are doing calculus or learning calculus at the moment, you will note that this means that, some things are constants and some things are not. So we might need to do, for example, a product rule or anyway, any of these particular rules. Okay, so this is the total pressure gradient is what we're solving for here. And by total, I just mean it includes all the possibilities, right? So here I got dp dx and equals. Now what I'm going to do over here, because it's going to make my life easier, is I'm going to distribute this rho g. So rho gh minus rho gz. Okay, cool. Keeping in mind that rho is a function of x, h is a function of x, rho is a function of x. Okay, those are all the things that are functions of x. Okay, so dp dx equals. Okay, so let's see. Let's pull that g right out because it's not a function of x. G. Now, I'm going to show you all the steps because otherwise I can skip steps, and that isn't necessarily a good thing. Okay, so I've got rho h right there. That's not a very good looking rho. So let's cancel it and let's make a better rho. Okay, both of those things are a function of x. Both of those things change in the x direction. Okay, and then we're going to do minus. Let's see, in this case, what can I pull out? The g is not a function of x, and the z is not a function of x. So I'm going to end up with gz d rho dx. And that's interesting. Okay, cool. So I didn't think it was going to all kind of fall out like that just yet, but here we go. We've got a term here. We'll have to figure out what to do with that, but we're still working on this other one. So let's keep working on it. So dp dx equals, let's see. So I'm gonna have to do a product rule here, right? Because I've got both of these things going on here, right? So let's see here, G, let's see. So we'll take the, we'll leave the rho alone first. G rho dh dx plus, and then G, and now I'm gonna leave the H alone, GH d rho dx, okay? Minus gz d rho dx. Okay, so we're just taking a nice big huge derivative here. So dp dx, again, this is the total pressure gradient, equals, let's see, maybe we can combine these two terms right here because they both have d rho dx, right? So we're going to have g rho, actually that's usually written as rho g, so let's go ahead and let's start making this look how it normally looks, dh dx plus, and this one's a little uglier, g. So I'm going to pull the g out, and I'm going to pull the d rho dx out. And we're left with xh minus z. Okay. So this is the result we were looking for, unless I've made some errors, which is always possible. Okay, and for you, this looks really confusing, I'm sure, but this is the pressure gradient. So this is how the pressure varies in the x direction, right? So this is the slope of the pressure in the x direction, essentially. Okay, this one right here and this one right here are different things. So I think hopefully you can see that this dx, so if I go back and I redraw my little imaginary river, here's my imaginary river, h is the total depth here. So this is h, okay, this is h. Okay, so that dh dx is the slope of the free surface. Okay, so this right here is called the barotropic pressure gradient. Okay, and because I hate random capital letters. So there's the barotropic pressure gradient. So that's the pressure gradient due to the fact that the free surface is sloping. Now, I think what's interesting here to note is that this is not a function of z, right? So it is the same, the pressure gradient is the same no matter where you are in the water column. So in other words, this pressure gradient, if I were to plot it, it looks like this, okay? And it doesn't vary vertically, okay? It's always the same. Okay, and of course, if you remember back to that video that I did, the second video, then that comes out, right, logically. And the only thing it depends on is the slope of this free surface, which is not constant in the x direction. It might change as you move to the right or to the left, but whatever. Okay, so that's cool. All right, so now what is this then? I hopefully you've figured out already this is going to be the baroclinic pressure gradient. Okay, and basically it depends on the change in the density in the x direction, right? So, so where the barotropic depends on how the h changes in the x direction, the baroclinic depends on how the rho of the freshwater or rho of the saltwater. I guess it doesn't have to be saltwater, but it can just be any reason that you might have a different density. So it could be because of heat or sediment in the water or who knows what else. But for some reason, we've got a pressure gradient going from a density gradient going from x to y. Now, what's really interesting and important about this one is to note that this is a function of z, right? So if you notice that we've got this little bit right here, h minus z. Okay, so h minus z, if we remember correctly, what is h minus z? Let's go all the way back up here. Oh, look at this, h minus z. So that's just the depth. That's the distance you are from the surface. Okay, so in other words, the farther you are from the surface, the greater this pressure gradient is. Okay. So if we go down here, we will notice that this pressure gradient, it looks something like this. The further away from the surface you get, the greater this pressure gradient is. Okay, and again, of course, I put that H right in the wrong spot. Okay, so again, just like earlier, we can draw, a kind of a, how did these two pressure gradients add up? If we add them together, we get the total pressure gradient, which, I'm going to color code this because, I like that kind of stuff. And it's going to, generally speaking, be in at the surface and out at the bed. Okay. Right, so it's going to be something like that. So that's if I add up the two pressure gradients. Baroclinic. So this is the the barotropic and the baroclinic. Okay, so hopefully you can see the power of this, that I was able to fairly quickly derive an expression which also quantifies the pressure gradient, the total pressure gradient in any system. It depends essentially on two things, really. Those two things are the free surface slope and how much the density is changing in the x direction. Okay, and that's how we could get at. And then once you had that, if you wanted to know what it was at a particular depth, well, you could just kind of play with this right here, right? Or if you wanted to put it on another planet, you wanted to play with G, you could do that. Okay, now there is one thing that I did want to mention before I got off of this particular topic, and that is that this is very, very, very powerful. Obviously, hopefully you can see the power of all this and how quickly this got to a solution. Or however, I wanted to make a point that it hits some hiccups because d rho dx isn't necessarily a nice easy thing to find. H dx is not necessarily easy to quantify. And there's all kinds of reasons why that would happen. So, for example, the river coming down, usually it kind of has a shape like this, right? Because the bed of the river kind of goes like this, and then you get out into the Gulf of Mexico, and it kind of does like that, right? And the Gulf of Mexico, the free surface is more or less flat. So here's the Gulf of Mexico, here's the Mississippi River, right? So hopefully you can see that dH dx is not constant, does not equal some sort of constant. Like you can't just say like, oh, it's, 10 to the negative 10 to the minus 7th or something, right? The depth is changing, and it's changing, the total depth is changing, and, it's not a constant number at the rate at which it's changing, right? So therein lies a rub. The other thing, of course, is that the salinity, right? So way upriver, we might expect to have a salinity of like, salinity is 0 way upriver. Okay, and then if you get down to the ocean, well, the salinity is 35. PSU is practical salinity units or parts per thousand. And there's lots of reasons why the, and in fact, interaction with all this stuff that we've already been talking about creates, for example, these nice, we might have a salt wedge estuary where the lines kind of do like this. Okay, and then all of a sudden, your d rho, your d rho dx is not a constant. Okay, let's say if this was constant 1, this is not constant 2. It's just not a constant. So it makes this particular expression, while very powerful, a little limited, right? Because the fact that this pressure gradient exists is going to create, is going to interact with the d rho dx to create kind of interesting situations. Okay, so just be aware of that there is tremendous power in this expression, but it is also limited. Okay, the real world is more complicated than our mathematical models. So this is a really nice model of an estuary. Okay, anyway, I hope that's helpful. So we're almost at 20 minutes, so hopefully you enjoyed it. All right, so I think this is probably the main picture right here. All right, see you guys. All right, bye.